Hello everyone, my name is Stephen Hassanbelli, and today I'll be redoing part 3 of the Ansys Fluent analysis project 1 for fundamentals of aerodynamics. We get started by creating a new fluid flow fluent project, and we can rename it part 3A. Right click on geometry and click new design model or geometry. All right, click on the Z-axis so we can be normal to the XY plane and click on New Sketch. Click the Sketching tab and Rectangle. And for our dimension, we'll be generating a 20 meter by 20 meter rectangle with a 1 meter circle, all of that centered at the origin. All right. There we go. 20 meters. We just got to make sure that everything is centered as well. 1 meter for the circle, and now we hit a vertical. And horizontal. Ten as well. Once we do that, we click on concepts, surfaces from sketches, sketch 1, hit apply, and generate. There we go. And now we can simply exit out of this and get back on our workbench. Double click on mesh. All right. So here we can start by naming all of our boundaries, and you can use the N key as a shortcut for it. I'm gonna click on type inlet. You can select 2 edges at a time as well. There we go. And here we can see all of our name selections as well. And now we proceed on the meshing phase. There we go. On element size, I have put in 3e to the -2. Then right click on mesh and click on method. And we're gonna select this face and hit apply. For our method, we're gonna do triangles, and I've noticed that it's way faster than the other option, the quadrilateral dominant. This one tends to mesh a lot faster. Click on mesh again, insert, and click on inflation. Now we're gonna click this face again. And for our geometry selection here, gonna click our cylinder. There we go. This one, we're gonna change it to total thickness on number of layers. I put in 50 for growth rate 1.1. And our maximum thickness, we're gonna set it to 0.1. There we go. And now we can hit generate. This should generate roughly around 932,000 elements. It might take a little bit, but it will yield a much better result at the very end. There we go. Now, if we click mesh again, there we go. And this is our mesh, by the way. It's very fine. If you click under statistics, we can see that it is, in fact, 932,000 elements. And if we zoom in, we can see how fine this mesh does get. There we go. Now we can exit out of this. Right click on mesh and hit updates. There we go. Once we do that, we double click on setup, hit double precision. And for people not having the full version of Ansys, you might be limited to 4 processors, but I can put in 16 because I do have the full version. And we're going to wait for it to load up properly so we can see all of the rest of the menu items. There we go. We're going to go under models, double click on viscous. And for part A, we're going to be analyzing an inviscid flow. There we go. And for our materials or fluid, I'm going to be leaving my density as it is. There we go. For our boundary conditions, for our inlet, I'm going to type in 5 meters per second. Outlet. We're going to prevent the reverse flow of it. And for our walls, we're going to change our wall type from a wall to symmetry. And we're going to leave the rest as it is. We're going to double check our reference values because these sometimes don't update and it can mess with your results and also with your simulation. And under methods, we're going to change the scheme to simple and the pressure to presto. And the reason why we do this is because sometimes, for whatever reason, there's weird artifacts that get generated during simulation. And even though it's an Inviscid flow, you will still get a wake region behind the cylinder, which should not be happening. But changing the scheme and also the pressure to presto does help with that. Under initialization, oh, hold on a second. We also need to change our residuals here. And I like to use 1e to the -6. There we go. And under initialization, I like to put in a couple more iterations just to have it start better. And we're going to click on initialize. There we go. We can double click on run calculations, change the number of iterations to 500. There we go. Once that is done, we can click on calculate and we can start our simulation. Crossing now the halfway mark. There we go. And the solution did not reach my convergence limit, but if you guys run it at a couple more iterations, it should eventually go down and converge to that residual condition. But 500 iterations should still nonetheless be okay, even at that higher residual, which, what was it? 3, -4 is still pretty good. There we go. We're going to click on OK. And now we can generate some plots straight from Fluent. I'm going to click on plots here. XY plot. We're going to name this one velocity on surface. Change it into velocity, and you can either choose to have it as a direction vector or as a curve length. Make sure you also select cylinder, and I'll show what the difference will be. Hit on save plot, and this is the direction vector. If you do curve length instead, it will simply be 2 of those. There we go. Close, and now we'll make a new window, and we'll generate a new plot again. This will be pressure coefficient. Surface. Go. Up here, you can change it from static pressure to pressure coefficient, cylinder, and hit save plot. Now, for both of these plots that we generated, you will have to write it to a file and click on write, and you can rename it. It will export as a .xy file. You will need some post-processing to turn it into a CSV file to then analyze it in Excel. I would also not sort the values because they can become a little bit weird. Just use them as they are from the XY file. I'm not going to generate this file now because I already have it, but you will need to do it for both plots, both for CP on the surface and also velocity variation on the surface. Now, the last thing we need as well is to get the drag coefficient. We're going to do that by going into report definitions. We're going to create a new definition, a force report, drag. Drag coefficient will be already selected up here. Just make sure you click on cylinder, and you can either hit compute and it will bring it out here immediately, or you can just simply hit on OK, close it up, and you can right click on this and hit compute from here, and it'll do the same exact thing. And our drag coefficient right now is 0.00258. Now for an Inviscid flow, it should be 0, but due to the nature of analytical systems like Ansys, it's really hard to get theoretical values, but we can definitely get approximations for it. Okay, and now that we've done this, we can exit out of Fluent. And we can double click on results. There we go. Now we can normalize it to the XY plane and create our contours. Click up here for contours. We're going to generate our velocity contour. For location, hit symmetry 1. In variables, select velocity, number of contours 200. And there we have it. There's no wake region, just like a Inviscid flow predicts. And we have an even and symmetric distribution of the velocities. Now I notice, I did notice it previously that for whatever reason, if you zoom all the way in, there is a boundary layer being generated. This is just an artifact, and it's not supposed to be here. But for whatever reason, whenever you open up the results in CFD-Post, um, this will have a boundary layer up here. The finer the mesh is, the lower this boundary layer will be, but it's still um, it's still gonna be there. And unfortunately, if we did decide to plot the velocity variation on the surface in CFD-Post, we would get um, 0, like a simple straight line, which is not good in our case. It would be if this was a viscous flow, but this is Inviscid, so it wouldn't count, which is why we have to export all of our data from Fluent and not CFD-Post. Now we can continue and generate our pressure contour. There we go. All right. Deselect this one. Location symmetry 1, pressure. And there we go. And here we can see the same thing again. Okay, and lastly, we can also generate all of our streamlines. And that will be this button right up here. And we're going to start this from the inlet. And we can also increase the number of our points. There we go. And we can see how the streamlines go right around the cylinder and connect back together back here. We can also increase the number of points as well. There we go. Okay, so this was our Inviscid case, which was part A. And now we can close out of this and continue with part B for our viscous laminar flow. And to do that, we're not going to recreate geometry and also a mesh. We're just going to reuse it. And to do that, we're going to click on setup once, right click, and we're going to hit on duplicate. And this will transfer over geometry and mesh and also the setup, but we can also just simply change it by double clicking into it. Same thing here, double precision, and select as many cores as you can. There we go. Under models this time, we're going to change this viscous model into not laminar, because for whatever reason, it just won't generate what I was expecting from it. But we're going to click on K omega instead. And don't worry about any of the other values. Just click OK. There we go. We're going to go under materials and fluid, um, this time we'll be seeing viscosity values as well as density values. I'm not going to change these again. I'm just going to leave these as they are for air. But what I will change is my free stream velocity. And I calculated a Reynolds number of about 205,000 if I use a 3 meter per second inlet velocity. And once again, we're gonna double check our reference values, change it to 3. All right. And for our methods, again, we're gonna switch it back to coupled and also second order. And our residuals should have carried over. Yes, they did. We can leave these, doesn't really matter. There we go. We're gonna double check this really quick. We still have 25, so we can initialize it. And after that is done, and we can simply start the calculation. And once again, we could have also double checked all other menus as well, but because we had duplicated over the previous project, part A, most of the things did carry over, so I didn't need to change the wall types to symmetry, for example, or prevent the reverse flow and the outlet and all that kind of stuff. we go. And we're almost at the end here. We can see that after about 300, 350 iterations, the solution started to plateau, and it didn't really change much. I still decided to wait for the full 500 iterations just to give it a little bit more time to process. There we go. So now we can generate our plots again. There we go. We're going to double click on this. And for the velocity, variation on the surface, I'll show it to you, even though I just named it CP, you'll understand really quickly. For the velocity, it's not going to change at all because it's a viscous flow, so it's simply going to be a straight line, right? So I wouldn't even bother to write a to file just because it's going to be a simple 2-point table on Excel. You can just simply put in, what is it? Negative 0.5.1 velocity 0, and the second point will be 0.5 velocity 0, and you can just graph that just to make it easier, because you'll have to post-process these numbers anyways. But for the pressure coefficient, you'll still get a pressure coefficient, and you'll see that it looks slightly different compared to the Inviscid case. And this is what you'll still need to export and write to file, and again have to post process this .xy file into a CSV to import it into Excel. And again, I wouldn't sort it just because it starts creating weird edges. And the reason for that is because there's technically 2 lines on here, because it's graphing both, it's plotting both the upper surface and also the lower surface of the cylinder. So that's why it would create 2, there is 2 lines here technically, and if you sort them all, it's gonna not treat them as separate, but it's gonna try and go from one point to the other. And if these 2 lines are slightly different, it will create those edges. So that's why I did not sort them out in Excel. Okay, so now we can go back to report definitions, generate a new force report, drag, CD, click on cylinder. And earlier I just clicked OK, but I'll just hit compute here, and you'll see that it populated down here right away. And click on OK, close. And again, you can just compute it from here, and it'll generate the same number. And we can see that the CD for this cylinder in a laminar case, it would be 0.54. And we'll see how that changes for the turbulent flow. But for now, we'll still finish processing this case here. We'll exit out of Fluent. Wait for this to finish up. If you ever needed to access that simulation again, don't double click on setup, because it's not going to save the results and all the values that you got. Just double click on solution instead, and it will be it will import again all of the solutions that it got from the simulation from those 500 iterations. So that way you don't have to wait on 500 iterations again. If you double click on setup, you'll have to redo the simulation. But for now, we'll just go into results. And we'll generate again the velocity contours, pressure contours, and the streamlines. Wait for this to load up. And right down here, you can already see that it's already generating them along with the streamlines, right? It's because we had duplicated them earlier. So There's no need for me to even go through them again because number one, I will do it again for you. We'll still take a look at them. There we go. So we can see the wake region down here, which is what we would be expecting from a laminar case. And you can see how the wake region doesn't necessarily merge back again. It separates completely. And we'll see how that's different for the turbulent case. Here's the pressure contours. And we'll take a look at the streamlines one last time. There we go. You can see this very big wake region. Okay, so now we can proceed on part C. And we'll do the same thing again. We'll just right click on setup, duplicate. Oh, and here, I forgot to rename this part 3B. And this will be, you see, there we go. We'll just double click on setup. Start. And again, most of the settings will be carried over because we're duplicating the projects. But there still is a couple of things we need to change in order for this simulation to become a turbulent flow. And as soon as this loads up, we can make those changes real quick. There we go. All right, and this time, this will be the general page, right? But if you're not on it, just double click on this and this will show up. Change the time to transient. I found that that is what makes a pretty big difference in how the wake gets generated afterwards. For the viscous model, we'll just still leave it at SSTK omega. And for the boundary condition, we'll be changing our inlet velocity from 3 meters per second to 10 meters per second, which will yield a Reynolds number of about 684,000, which is well above the transition region. There we go. We'll change that. We'll change the reference value again to 10. And for the methods, we'll leave everything as it is. And now, because we also changed the time to transient, this will have changed as well. We'll just put it back on hybrid and leave it at 500 iterations. We're going to go on calculations. Maximum number of iterations, 500. And again, just make sure you don't put it in here because it'll go for a very long time. We just want it to stop at 500 iterations. And we can proceed with our calculation. Oh, forgot to initialize it, right? We can always just do this, initialize and calculate from here. There we go. So initialize it, it'll do the first 25 iterations. And here starts our simulation. There we go. And this calculation is complete as well. And we can do the same thing again as we did earlier. We can generate our report, go new, drag, CD, click on cylinder. And we can see already that in the turbulent case, uh, it's about what, 24%, something like that. Lower compared to the laminar case. I think it was like 0.54 and this is 0.40, which matches up. And we'll take a look at the velocity contours later on as well. We'll generate our CP surface plot. And again, make sure you just export these data points. Change this to pressure coefficient on the cylinder. And just so we can see it. There we go. We'll just close this. And here you can see what I was talking about earlier with there being two lines. And because this is a turbulent case, there will be more velocity variations and also pressure variations throughout the surface. In this case, highlights the fact that there is indeed two curves and that Fluent indeed does plot them over both the upper surface and also the lower surface as well. Okay, so now that we have this, and I can also quickly show the velocity and just to show that it is indeed zero. There we go. Same thing again. Okay. Now, once this is done and that we got our CD values, we can close out of Fluent. And we can open up our CFD-Post and take a look at our contours. You can still look at the contours from Fluent as well, but I just prefer looking at them on CFD-Post. And this, most of the time, will not turn green. Still not exactly sure why, but it still won't prevent you from opening up the results in CFD-Post. Go, and now it's going to generate all of our contours really quick. Let it load up, and here we can see the streamlines. Turn this off and look at our velocity contour. We can see that the wake region joins back in and there's less of a separation in the wake region compared to the laminar case. Take a look at the pressure contour as well. And just to show it, I guess we can also just open up the laminar case as well. Take these off, put on velocity contour. We'll click this too. There we go. So this is the turbulent case, and this will be our laminar case. You can see the big difference in the wake region that there is. And this will, of course, generate a lower CD. There we go. And that will be it for the project.